A star dies, and the universe holds its breath. In that final, catastrophic collapse, a stellar giant vanishes, leaving behind a legacy of cosmic puzzles. We are about to journey through 30 profound mysteries hidden within these spectacular stellar deaths. By the end, you will possess a new understanding of the forces that forge the elements of life and shape the cosmos itself. We will confront the ghostly particles that carry a star's last scream and question what strange object is left spinning in the wreckage. What secret about our own existence is written in the light of a dying sun? Deep within a massive star's final hours, a silent battle rages at its very heart. For millions of years, the core has fought a relentless war against gravity, fusing lighter elements into heavier ones to produce the outward radiation pressure that keeps the star inflated. This delicate balance shatters when iron begins to accumulate. Iron fusion is a cosmic thief. It does not release energy, it consumes it. With this final power source extinguished, the core's primary defense against its own immense weight vanishes. In less than a single second, the stellar heart gives way. The core, once a blazing sphere of plasma, is now crushed inward by gravity's unopposed grip, collapsing at speeds approaching 1/4 the speed of light. This is the precipice of stellar death, the precise trigger we struggle to define. Our best models point to the Chandrasekhar limit, a critical threshold of about 1.4 times the Sun's mass, where a white dwarf star would meet a similar fate. But for a massive star's core, reaching this point of instability is a quantum mechanical dance. We cannot pinpoint the exact moment of collapse because it involves the sudden, unpredictable failure of a quantum pressure exerted by electrons, a last-ditch effort to hold up the core. When even this fails, the star has passed a point of no return, and the countdown to a supernova begins. That catastrophic collapse unleashes a flood of ghostly particles, the universe's most elusive messengers. As the stellar core is crushed into an impossibly dense sphere, its protons and electrons are forced together, merging into neutrons and releasing a torrent of neutrinos. In that single, violent second, more neutrinos stream out than there are stars in the observable universe. They carry away 99% of the star's entire gravitational energy, a staggering release of power that should, in theory, be the very engine that blows the star apart. This is the neutrino-driven explosion mechanism, the leading model for how a core collapse supernova reverses its own implosion. Yet here we find our second great mystery. When we point our most sensitive detectors at a nearby supernova, like supernova 1987, in the Large Magellanic Cloud, the number of neutrinos we capture is far lower than our models predict. This is the neutrino luminosity problem. Where is all that missing energy? It is as if we were standing outside a powerhouse, hearing the roar of its generators, but only feeling a faint breeze from its exhaust. One possibility is that our understanding of neutrinos themselves is incomplete. These particles are notorious shape-shifters, oscillating between different types as they travel. Perhaps within the unimaginable densities of the collapsing core, they are transforming in ways we have not yet anticipated, effectively trapping a portion of their energy inside the newborn neutron star. Another, more profound idea is that the neutrinos are not the only players. Could an unknown particle, something even more ghostly and difficult to detect, be siphoning away a share of the star's final breath? The answer is locked within the next dying star, a cosmic event that will force us to rewrite the rules of both stellar death and fundamental physics. This outward surge of neutrinos is only half the story. The true mystery lies in how that energy transfer actually rips the star apart. We call this the supernova mechanism, and it represents the single greatest failure of our computational models. For decades, the leading theory has been the neutrino-driven explosion. The idea is that a small fraction of these ghostly particles, perhaps just 1%, deposit their immense energy into the infalling layers of the star above the core. This heats the gas, creating a raging bubble of turbulence that can, in theory, reverse the collapse and blast the star's outer envelope into space. It is a beautiful and elegant concept, a stellar phoenix rising from a neutrino fire. Yet when we try to simulate this process on the most powerful supercomputers, the explosions are often weak or they fail to happen at all. The neutrinos seem to escape too easily, leaving the star to implode silently into a black hole. So what is missing from our models? One compelling alternative is the acoustic mechanism. This theory suggests that the real driver is not a steady neutrino heating, but a series of powerful vibrations. The newborn neutron star at the center is not a still object, it is ringing like a colossal bell. These vibrations, these seismic waves, pump enormous amounts of energy into the stellar material. It is as if the star's own heart is beating so violently that it shatters its own body from the inside out. But even adding this sonic fury does not always produce a successful explosion in our simulations. The problem is one of unimaginable complexity. We are trying to model a chaotic, three-dimensional environment where fluid dynamics, nuclear physics, gravity, and particle interactions all collide in a fraction of a second. A single miscalculation in how turbulence behaves on a small scale can doom the entire virtual star to a failed death. This is why the core collapse supernova mechanism remains one of the grandest unsolved problems in all of astrophysics. We know the star explodes, we see the brilliant proof in the night sky, but we still cannot reliably make it happen inside our computers. The universe is holding back a crucial piece of the recipe, a secret ingredient that turns a collapse into a cataclysm. Even our most beautiful simulations of stellar death are a lie. We model these explosions as perfect, expanding spheres of fire, but the universe is far messier. Look at the shattered remains of Cassiopeia A, a supernova remnant whose light reached Earth just over 300 years ago. It is not a serene bubble, it is a chaotic, lopsided wreck. Clumps of iron and silicon have been blasted out in one direction, while other elements seem almost left behind. This is the fourth mystery, the puzzle of asymmetrical explosions. Why do stars die in such violently unbalanced ways? The answer seems to lie in the final moments of the core itself. In that ultimate collapse, the newborn neutron star is not a placid sphere. It is a roiling, turbulent environment where convection creates massive plumes of hot matter rising and colder matter falling, like a pot of water boiling over an inferno. This internal chaos alone can seed an uneven explosion, but two other forces can take this imbalance and turn it into a full-scale directional blast. The first is rotation. If the star's core was spinning rapidly before it died, its collapse will accelerate that spin dramatically, the same way a figure skater spins faster by pulling in their arms. This can focus the explosive energy into powerful jets erupting from the poles. The second, even more dramatic force is magnetism. When a rapidly spinning core is wrapped in incredibly strong magnetic fields, those fields can get wound up trillions of times, transforming the supernova into a hyper-powered engine. The result is not a mere explosion, it is a cannon shot. This violent asymmetry has a profound consequence. It gives the resulting neutron star a tremendous kick. Like a rocket with a plugged nozzle suddenly bursting free, the neutron star is launched away from the site of its own birth at speeds exceeding 1,000,000 miles per hour, a runaway celestial cinder hurtling through the galaxy. This explains why we find so many of these dense stellar corpses far from the galactic neighborhoods where they were born. Their very formation was an act of cosmic recoil, a final, unbalanced shudder from a dying star. That violent kick sends the neutron star flying, but it leaves behind an even deeper puzzle. We look at the site of a supernova and ask a seemingly simple question. What kind of star was that? This is the progenitor problem, and it is a mystery that strikes at the very heart of stellar evolution. For years, we believed we had a clear rulebook. Only stars more massive than about 8 times our Sun would end their lives in a core collapse supernova. We have even been fortunate enough to point the Hubble Space Telescope at galaxies before a star exploded, and then gone back to look at the pre-explosion images to find the doomed giant. Sometimes we find it, a massive, bloated red supergiant, exactly as predicted. But in other cases, we look at the precise location and we find nothing. The star that was supposed to be there has simply vanished from the archival photos. It is a cosmic ghost, a stellar disappearance that defies our expectations. Where did it go? The leading theory is that these missing progenitors were not the classic red supergiants we imagine. Perhaps they were stars that had been stripped bare. In a binary star system, one star can gravitationally siphon away the outer hydrogen layers of its companion, leaving behind a naked, hot helium core. This stripped star would be much smaller and fainter than a red supergiant, easily hiding from our telescopes until its final, brilliant demise. Another, more dramatic possibility is a stellar merger. 2 stars could have spiraled together and coalesced into a single, unstable object just before the explosion. This chaotic event would create a star that our models of peaceful, solitary evolution never accounted for. The implications are profound. It means our census of potential supernova progenitors is incomplete. The universe is not just killing off the obvious massive stars. It is also ending the lives of strange, hidden, or reshaped stars that we do not yet know how to properly classify. Our rulebook for stellar death is missing entire chapters. These asymmetrical blasts point to a hidden architect, a force that can sculpt chaos into a focused beam of pure destruction. This is the role of magnetic fields, the 6th and perhaps most volatile ingredient in a star's death. During the core's catastrophic collapse, its primordial magnetic field is not just preserved, it is amplified beyond all comprehension. As the core shrinks from a sphere the size of Earth down to a city mere miles across, its magnetic field lines are squeezed together, intensifying their strength. In a spinning core, this process acts like a dynamo, winding those field lines into a tight, coiled spring of energy. The result is a magnetic field that can reach 1 trillion times the strength of Earth's own protective shield. To stand near such an object would be fatal in a way that defies physics. Your very atoms would be torn apart by the field's sheer force. These are the conditions that birth a magnetar, a neutron star with a magnetic field of almost unimaginable power. But their influence may reach far beyond their immediate vicinity. We suspect that these ultra-strong magnetic fields are the central engine behind the most violent explosions in the cosmos since the Big Bang itself, the long gamma-ray burst. In this scenario, the collapsing star does not just explode, it transforms. The intense magnetic fields channel the star's dying energy into 2 narrow, ultra-fast jets that drill their way out through the stellar poles. If one of these jets is pointed directly at Earth, we see it as a brilliant flash of gamma rays, a beacon of stellar annihilation visible across billions of light years. The star is not just dying, it is screaming its end into the cosmos with a focused magnetic roar. This magnetic shaping continues long after the initial explosion, sculpting the expanding debris into the intricate filamentary structures we see in supernova remnants. The field acts as an invisible scaffold, guiding the flow of hot gas and high-energy particles, creating the beautiful, ghostly nebulae that mark a star's grave. The mystery we now face is one of origin. What determines whether a dying star becomes a magnetar, a quieter neutron star, or something else entirely? Is it the star's initial spin, the strength of its inherited magnetic field, or a chaotic interplay of both? We are only beginning to understand how this invisible magnetic hand writes the final signature of a stellar collapse. These magnetic monsters are not the only possible outcome of a stellar collapse. Sometimes the death of a star is so complete, so utterly catastrophic, that it dwarfs even the most powerful supernova. This brings us to the seventh mystery, the birth of hypernova and their associated gamma-ray bursts, the most luminous explosions in the universe since the Big Bang. At the heart of these events lies the collapsar model, a scenario of total stellar annihilation. In a typical supernova, the core collapse is halted, creating a neutron star. But for the most massive stars, that collapse does not stop. The core's gravity is so overwhelming that even the neutron star's quantum pressure fails. It continues to implode, crushing itself past any conceivable density and forming a black hole directly from the star's heart. This is not a slow feeding process. The black hole is born in an instant, surrounded by a vast, dense, and rapidly spinning disk of leftover stellar material. It is from this cosmic maelstrom that the true violence emerges. As matter from the disk spirals into the black hole at near light speed, immense magnetic fields and friction heat it to temperatures of billions of degrees. This process powers two narrow, incredibly energetic jets of plasma and radiation, firing away from the black hole's poles at over 99.9% the speed of light. These are relativistic jets, so named because their behavior is governed by Einstein's theory of relativity. If one of these celestial blowtorches is pointed fortuitously in our direction, we detect it as a long gamma-ray burst, a flash of high-energy light that can outshine entire galaxies for a minute or two, yet originates from a region perhaps no larger than our solar system. The question then becomes, why are these events so rare? Only a tiny fraction of collapsing stars produce a gamma-ray burst. The recipe requires a perfect and terrifying storm of conditions. The progenitor star must be exceptionally massive, likely over 40 times the mass of our Sun, to guarantee the direct formation of a black hole. It must also be rotating extremely rapidly. This fast spin is crucial for creating the accretion disk around the newborn black hole, the very engine that powers the jets. Without this spin, the infalling matter would simply be swallowed whole and the jets would never form. Finally, the star must have low metallicity, meaning it contains very few elements heavier than hydrogen and helium. Such stars lose less mass through stellar winds during their lives, allowing them to retain their massive, rapidly spinning cores right up to the moment of collapse. It is this precise combination of immense mass, rapid rotation, and primordial composition that forges a collapsar, turning a stellar death into a universe-spanning beacon of pure energy. The rarity of these events is a testament to the fine line between a brilliant supernova and a truly apocalyptic hypernova. The violence of a hypernova is almost beyond comprehension, yet it may be the very source of the most precious materials in our world. Scattered within the expanding debris of these stellar explosions are the seeds of planets and life itself, atoms forged in the most extreme conditions the universe can offer. This is the cosmic alchemy of the rapid neutron capture process, or the R process, the eighth mystery of collapsing stars. It is the mechanism responsible for creating roughly half of all the elements heavier than iron found in the universe, including the gold in a wedding ring, the platinum in a catalytic converter, and the radioactive uranium that heats the Earth's core. The process is brutally simple in concept, yet fiendishly difficult to achieve. It requires an environment with an immense flood of free neutrons, subatomic particles with no electric charge. In this neutron-rich soup, an atomic nucleus like a seed of iron can be bombarded. Before it has a chance to radioactively decay, another neutron slams into it, then another and another in a rapid, violent cascade. This forces the nucleus to grow impossibly heavy, far beyond the elements found in nature. This overstuffed, unstable nucleus then undergoes a series of radioactive decays, transmuting itself into a stable, heavy element like gold or platinum. The entire sequence can happen in a matter of seconds, transforming common elements into rare, precious metals. For decades, the leading candidate for this cosmic forge was the very supernova explosion we have been exploring. The theoretical models suggested that the intense neutrino wind blowing off the newborn neutron star could create the perfect neutron-rich environment in the outer layers of the collapsing star. It was a beautiful, self-contained story. A star dies, and in its death throes, it manufactures the building blocks for future worlds. But then, the observations began to challenge this elegant idea. When we looked at the elemental composition of very old stars, some of the first to form in the galaxy, we found they contained signatures of our process elements. This was puzzling. If supernova were the primary source, the distribution of these heavy elements should be more uniform, but it was not. They appeared in clumps and strange patterns, suggesting a rarer, more violent production site. The focus then shifted to an even more cataclysmic event, the collision of two neutron stars. In 2017, we witnessed this directly for the first time. The LIGO and Virgo gravitational wave observatories felt the space-time ripples from such a merger, and telescopes across the globe swiveled to see the aftermath, a phenomenon known as a kilonova. The spectroscopic data was definitive. The expanding glow was rich with the telltale signs of lanthanides and other heavy elements, including vast amounts of gold and platinum, forged in the turbulent debris of the collision. The calculations were staggering. A single neutron star merger can forge an amount of gold equal to hundreds of times the mass of our entire planet. So where does the R process truly occur? The answer is likely both. Some supernova, particularly those that produce highly magnetized neutron stars or that undergo a specific type of delayed explosion, might still contribute a share of these heavy elements. But the spectacular neutron star mergers seem to be the universe's ultimate heavy element factories, rare events that seed entire galaxies with the materials for complex chemistry and ultimately for life. The mystery is no longer just about how these elements are made, but which stellar death sentence writes their recipe most often. Our very existence is tied to the answer, for we are all quite literally stardust forged in the crucible of cosmic catastrophe. This cosmic alchemy leaves behind a dense cinder, the final monument to the star's life. But the nature of this remnant is one of the most pressing questions in astrophysics. Does the collapse forge a neutron star, or does it continue into the absolute oblivion of a black hole? The line between these two fates is incredibly fine, dictated by the final mass of the collapsing core. If the leftover core weighs less than about 2.2 times the mass of our Sun, the inward crush of gravity is balanced by a strange quantum force. The neutrons, packed together with almost no space between them, push back with a powerful degeneracy pressure, creating a stable, city-sized object of unbelievable density. A single teaspoon of its material would weigh billions of tons. This is the neutron star. But if the collapsing core is heavier than that critical threshold, perhaps 3 solar masses or so, no known force in the universe can possibly support it. The neutrons themselves are crushed out of existence, and the core collapses forever, forming a black hole. The boundary between these two outcomes, however, is not a clean line. It is a cosmic no-man's land known as the mass gap. For decades, our observations revealed a strange void. The heaviest neutron stars we found clustered around 2 solar masses, while the lightest black holes, detected by their gravitational pull on companion stars, started at around 5 solar masses. This left a puzzling gap between 2 and 5 solar masses where no objects were seen. What happens in this gap? Does nature simply refuse to make compact objects in this weight range? Or are they just exceptionally good at hiding? One possibility is that a collapsing core in this mass range might briefly form a neutron star, only for it to be unstable. It might endure for mere milliseconds before its own weight overwhelms it, succumbing to a final collapse into a black hole. Another, more exotic idea is that within this gap, matter transforms into something entirely new. Under such immense pressure, the neutrons might dissolve into a soup of their constituent particles, quarks, creating a stable quark star. We do not yet know if such objects truly exist, but they would represent a state of matter so extreme it defies our current physics. The very existence of the mass gap challenges our understanding of the ultimate fate of matter, forcing us to ask what happens when you compress a star's core beyond the limits of a neutron star, but before it vanishes completely into a black hole. That dense stellar cinder left behind is far from a placid orb. It is a dynamic, often temperamental object, and its behavior can reveal secrets locked deep within. Young neutron stars, especially those we observe as pulsars, are cosmic metronomes, their lighthouse beams of radiation sweeping past us with a regularity that can rival atomic clocks. But sometimes the clock skips a beat. Without warning, the star's rotation suddenly speeds up, spinning faster for a fraction of a second before settling into a new, slightly quicker rhythm. These events are called pulsar glitches, and they are the 10th mystery of collapsing stars. A glitch is a tiny hiccup in time, but it represents a massive release of energy from within the star's interior. How can an object with the mass of a sun packed into a city, an object so unimaginably dense, suddenly change its spin? The leading explanation involves a starquake. Picture the neutron star's surface not as a smooth, solid sphere, but as a crust of incredibly dense, crystalline atomic nuclei. This crust is under immense strain, forced into a spherical shape by the star's own gravity. As the pulsar spins, it gradually loses energy and slows down. This slowdown causes the star to become slightly more spherical, and its solid crust must adjust. Like the tectonic plates on Earth, the neutron star's crust can fracture under the stress. When it cracks and settles into a new, more compact shape, the entire star suddenly spins faster, the same way an ice skater spins faster by pulling their arms inward. This is the starquake model, a dramatic crustal rearrangement that literally changes the star's moment of inertia. But there is another, perhaps more profound theory that points to the bizarre nature of matter itself. This is the superfluid vortex unpinning model. Inside the neutron star, beneath the solid crust, lies a superfluid sea of neutrons. A superfluid is a state of matter with zero viscosity. It flows without any friction whatsoever. This neutron superfluid is also rotating, but it is threaded with countless tiny tornadoes of rotation called vortices. In a normal, steady state, these vortices are pinned to the solid crust, their rotation locked to the crust spin. As the crust slows down due to its energy loss, the superfluid inside wants to keep spinning at its original, faster rate. A tension builds. Eventually, the strain becomes too great, and a vast number of these microscopic vortices suddenly break free from the crust all at once. When they unpin, they transfer a massive amount of rotational momentum to the solid crust, giving the entire star a sudden speed boost. This event is like a gigantic internal avalanche of angular momentum. The glitch we observe is the moment the star's rigid exterior catches up with the faster spinning heart within. Studying these glitches gives us a unique probe into the internal structure of a neutron star. The way a pulsar recovers from a glitch, slowly relaxing back toward its pre-glitch spin rate, tells us about the friction between the superfluid core and the solid crust. It is our only way to conduct an experiment on matter at densities we could never hope to recreate on Earth. Each glitch is a telegram from the heart of a cosmic extreme, a message written in the language of spinning time and quantum strangeness. That stellar heartbeat, the steady pulse of a neutron star, should be the final signature of a supernova. Yet when we look into the expanding wreckage of these explosions, we often find a profound silence. This is the 11th mystery, the case of the missing neutron stars. We observe a beautiful, intricate supernova remnant, a glowing testament to a star's catastrophic death, and we point our most sensitive radio and X-ray telescopes directly at its center, searching for the telltale blink of a pulsar. But in many cases, there is nothing there. The heart of the explosion has simply vanished. Where did it go? The first possibility is the most dramatic. The collapse did not produce a neutron star at all. Perhaps the progenitor star was so massive that the collapsing core exceeded the neutron star mass limit immediately. Instead of a dense cinder, the collapse forged a black hole directly at the center of the explosion. A black hole, unless it is actively feeding on matter from a companion star, is utterly dark and silent. It would leave no pulsar signal, no beam of radiation to sweep past our telescopes. The supernova remnant would expand for centuries, a beautiful shell with a literal void at its center, a ghost in the cosmic machine. The second possibility is that a neutron star was indeed born, but it was born running. As we explored with asymmetrical explosions, the violent, lopsided nature of the supernova can give the newborn neutron star a tremendous kick. This is not a gentle nudge. It is a gravitational slingshot that can launch the stellar corpse at speeds exceeding 1,000,000 miles per hour. At such velocity, the neutron star would have long since rocketed out of its own debris cloud, traveling far into the interstellar void before the remnant had even expanded to a noticeable size. We would be left looking at the empty cradle, the beautiful remains of the nursery, while the child itself is already light years away, drifting unseen through the galaxy. There is a third, more puzzling scenario. What if the neutron star is still there, hiding in plain sight? It might be a pulsar whose narrow beam of radiation simply does not point toward Earth. From our perspective, it would be an invisible lighthouse, its powerful signal sweeping across the cosmos in a direction we can never see. Or it could have aged into a state of quietude. A pulsar's magnetic field is thought to weaken over millions of years, and as it does, its radio beacon slowly fades into silence. The neutron star becomes a cold, dark ember, still present at the heart of the remnant, but emitting too little radiation for our current instruments to detect. Each silent remnant is a cosmic crime scene, and we are the detectives left to piece together the fate of the stellar corpse. Did it collapse into ultimate darkness? Was it ejected into a lonely exile? Or is it merely sleeping, its heartbeat too faint for us to hear? The answer changes the final chapter of every star's life, forcing us to question what truly remains after the brilliant flash fades from view. But this entire story of collapse assumes a star has a core of iron to trigger its demise. What if the star is so monstrously large that its death comes from an entirely different kind of instability? We now encounter a theoretical giant, the pair instability supernova, an explosion so brilliant it could outshine an entire galaxy, and so complete it leaves absolutely nothing behind. This process begins in stars of truly staggering mass, between approximately 140 and 260 times that of our Sun. Deep within their cores, temperatures soar to billions of degrees, hot enough that the radiation itself, the very photons bouncing around, become participants in a catastrophic reaction. Normally, photons are massless particles of light, but at these extreme energies, they spontaneously transform. A high-energy photon can suddenly materialize into a particle and its antimatter counterpart, most commonly an electron and a positron. This act of creation is the star's undoing. Radiation pressure from these photons is the critical force holding up the star's immense outer layers. When photons vanish to become matter, that supporting pressure plummets. It is as if the foundation of a skyscraper suddenly turned to smoke. Without that outward push, a portion of the core experiences a partial collapse. This is not a collapse to a neutron star or a black hole. Instead, the compression heats the core even further, reigniting nuclear fusion in a runaway thermonuclear explosion. The entire star is obliterated, not just blown apart, but completely vaporized. No neutron star remains, no black hole forms. The star simply ceases to exist, scattering its enriched guts across space in the most luminous stellar explosion possible. The central mystery is whether these titanic events are real. For decades, they were purely a theoretical prediction, but then we began to see supernova that defied all other explanations. Events like SN 2006 GY were hundreds of times brighter than a normal core collapse supernova and lasted for months, their light curves and chemical signatures matching the models for a pair instability explosion. These observations suggest that the first stars in the universe, which were likely these behemoths, may have died in such spectacular fashion, seeding the early cosmos with the first heavy elements. Yet the evidence is not yet conclusive. Could another, even more exotic process produce such brilliant flashes? The hunt is on to find more of these cosmic fireworks, each one a potential testament to a star so massive that it was torn apart by the sheer energy of its own light. The brilliant flash of a supernova is just the beginning of its story. For months, even years, the fading glow of the explosion tells a tale written in light, a graph of brightness over time we call a light curve. Yet here lies our 13th mystery, for no two of these cosmic stories are ever exactly alike. Each supernova paints its own unique signature across the sky, a fingerprint of luminosity and duration that challenges our attempts at simple classification. At the heart of this variation is a radioactive powerhouse, nickel-56. This unstable isotope is forged in the intense heat of the explosion itself, and as it decays first to cobalt-56 and then to stable iron, it releases the energy that powers the supernova's long-lasting afterglow. The amount of nickel-56 created is the primary dial controlling the supernova's peak brightness. A massive production, perhaps a fifth of our Sun's mass in pure nickel, results in a dazzlingly brilliant event. A more modest synthesis leads to a fainter, more subdued farewell. But the quantity of radioactive fuel is only part of the puzzle. The geometry of the blast plays an equally crucial role. An explosion that is roughly spherical will release its energy in a smooth, predictable decline. However, if the explosion is highly asymmetrical, with jets and plumes of debris expanding at different speeds and in different directions, the light we see becomes a complex tapestry. Our view from Earth depends entirely on our perspective. Are we looking down the barrel of a jet, seeing the concentrated energy head-on? Or are we viewing the explosion from the side, seeing a broader, slower unveiling of its inner elements? This single factor can make two identical explosions appear completely different to different observers across the galaxy. Finally, the environment the explosion slams into can dramatically reshape its light. Many massive stars spend their final years shedding their outer layers in powerful stellar winds, creating a dense shroud of circumstellar material around themselves. When the supernova blast wave plows into this pre-existing shell of gas, it creates a spectacular secondary brightening. The kinetic energy of the expanding debris is converted into a new flash of light, a brilliant echo that can dominate the light curve for months. This interaction can make a supernova appear far brighter and longer lasting than its radioactive heart could ever manage alone. So when we observe a supernova's light curve, we are not just measuring a simple decline. We are deciphering a complex message about the star's explosive death, the elements it created, the shape of its destruction, and the very wind that blew from its surface in its final days. The incredible diversity of these light curves is a constant reminder that every stellar death is a unique and deeply personal event in the life of the cosmos. Sometimes the universe stages a brilliant deception. A star will erupt with the ferocity of a supernova, brightening to a staggering degree and casting its light across galactic distances, only to then fade away and reveal the star itself, wounded but still shining. These are the supernova imposters, and they represent a profound challenge to our understanding of stellar death. The most famous of these great pretenders is Eta Carinae, a hypergiant star system that, in the 1840s, underwent a colossal eruption known as the Great Eruption. For over a decade, it became the second brightest star in the entire night sky, ejecting at least 20 times the mass of our Sun in a titanic outburst. From our vantage point, it looked for all the world like a supernova. Yet when the cosmic dust literally settled, Eta Carinae was still there. it had survived its own apparent death sentence. What could possibly cause such a violent, non-terminal event? The leading suspect is a phenomenon known as the super-Eddington instability. Every star exists in a delicate balance between the outward push of radiation and the inward pull of gravity. For the most massive, luminous stars, that balance is perpetually on a knife's edge. If the star's core produces too much radiation, the outward pressure can overcome gravity not in a controlled flow, but in a massive, explosive surge. It is as if a pressure cooker's valve fails completely and the entire lid blows off. The star does not collapse, it simply explodes its own outer layers into space in a temporary, convulsive fit. In binary systems like Eta Carinae, the plot thickens. The gravitational tug of a close companion star can destabilize the primary star, potentially triggering or amplifying these violent mass ejections. The material thrown off in these events forms vast, expanding clouds of gas and dust known as bipolar nebulae that often resemble a cosmic hourglass, a testament to the directional nature of the eruption. These imposter events blur the line between a stellar outburst and a true collapse so completely that they force us to ask a fundamental question. Is a supernova imposter merely a failed supernova, a stellar cry for help that fell just short of total collapse? Or is it a distinct, recurring phase in the life of the most massive stars, a series of violent rehearsals before the final, fatal performance? Every time we witness one of these events, we are watching a star play with fire, teetering on the very brink of destruction without quite falling in. Falling to Earth from the depths of space, an invisible rain of atomic fragments constantly peppers our atmosphere. These are cosmic rays, subatomic bullets traveling at nearly the speed of light, and their origin is one of the longest-standing puzzles in astrophysics. For over a century, we have known they exist, but tracing their source has been like trying to find a single gunman in a battlefield where every weapon fires at once. The leading suspects in this cosmic mystery are the very stellar collapses we have been exploring. A supernova's expanding shockwave is a perfect natural particle accelerator. For thousands of years, this colossal shell of debris, traveling at millions of miles per hour, plows through the interstellar medium. The chaotic magnetic fields tangled within the remnant can trap charged particles like protons and atomic nuclei, forcing them to cross the shock front again and again. With each crossing, the magnetic fields give them another kick, a process known as diffusive shock acceleration, boosting their energy to a significant fraction of light speed. Eventually, these particles escape their magnetic cage, ejected into the galaxy as the very cosmic rays we detect. It is an elegant theory, and we see strong supporting evidence. The Fermi Gamma Ray Space Telescope has observed the telltale glow of supernova remnants, a specific type of gamma-ray light produced when these accelerated cosmic ray protons collide with slower-moving gas atoms. The remnants are clearly acting as cosmic power plants, yet a definitive conviction in this cosmic court has been frustratingly elusive. The central challenge is that cosmic rays are not like beams of light that point back to their source. They are charged particles, and as they travel across the galaxy, the Milky Way's own magnetic fields bend and twist their paths. By the time a cosmic ray finally reaches our detectors, it is impossible to simply trace its trajectory backward to a specific supernova remnant. It is like trying to find the origin of a leaf caught in a hurricane by looking at the spot where it finally landed. The highest energy cosmic rays present an even deeper enigma. While supernova remnants can explain most of the galactic cosmic rays, the absolute most energetic particles, the ultra-high energy cosmic rays, possess millions of times more energy than any human-made particle accelerator can produce. Their origin is almost certainly extragalactic, and it is doubtful that a standard supernova shockwave is powerful enough to create them. Could they be spawned by the even more violent hypernova and gamma-ray bursts, or perhaps from the environments around supermassive black holes? The mystery endures because the evidence is so indirect. we are left with a compelling but still circumstantial case. We have the motive, the supernova's immense energy. We have the means, the shockwave and its magnetic fields, but we are still searching for the smoking gun, the one specific cosmic ray that we can irrefutably link to the wreckage of a single, known dying star. The very elements forged in a star's death must eventually clump together, forming microscopic grains that will one day become the building blocks of new planets. This cosmic dust is more than just space soot. It is the essential ingredient for galaxy formation, the material that cools gas clouds and allows them to collapse into stars. For decades, we believed that core collapse supernovae were the universe's primary dust factories, especially in the early cosmos. The theoretical models were compelling. As a supernova's outer layers expand and cool in the years following the explosion, atoms of carbon, silicon, oxygen, and iron should condense out of the gas, much like water vapor forming snowflakes in a cold sky. These tiny solid particles, trillions upon trillions of them, would then be ejected into the interstellar medium, seeding future generations of star birth. We have even seen direct evidence of this process. Infrared telescopes have peered into young supernova remnants like Cassiopeia A, detecting the warm glow of freshly synthesized dust, amounting to nearly a quarter of our sun's mass. The factory seems to be working. Yet, when we look at the very first galaxies, a profound discrepancy emerges. Our observations of these ancient systems consistently show less dust than our models predict, often by a factor of 10 or more. This is the dust factory paradox. If supernovae are producing all this dust, where is it all hiding? The leading suspect in this cosmic theft is a phenomenon known as the reverse shock. Imagine the supernova blast wave as a colossal shell expanding into space. For centuries, it plows through the interstellar medium, but eventually it encounters resistance. The material it swept up early on begins to pile up and slow down, creating a powerful pressure wave that travels backward, back into the expanding remnant itself. This is the reverse shock, a destructive tsunami that washes back over the newly formed dust grains. Traveling at speeds of thousands of kilometers per second, this shock front slams into the delicate dust particles. The tiny grains, only a fraction of a micron in size, are heated to such extreme temperatures that they are vaporized back into individual gas atoms. It is a heartbreaking cosmic cycle. The universe giveth, and the universe taketh away. A dust grain that took years to form in the cool outer debris can be destroyed in an instant by this inward rushing wave. The mystery deepens when we consider that not all dust is created equal. Smaller grains are more easily destroyed, while larger, more robust particles might survive the reverse shock. This suggests that the dust we do see in the early universe might only be the largest, most resilient fragments that endured the apocalyptic cleaning process. Another possibility is that we are simply looking at the wrong time. Perhaps the dust production is not a single event but a slow, cumulative process. While a single supernova might lose most of its dust to the reverse shock, the combined effect of millions of supernovae over hundreds of millions of years could gradually build up the dust reservoirs we see in more mature galaxies. The survival of this cosmic grit is not just an academic curiosity. Without dust, gas clouds cannot cool efficiently enough to collapse and form the first stars and galaxies. The entire timeline of cosmic structure, and by extension our own existence, hinges on the solution to this paradox. Is the dust being destroyed, or are we fundamentally wrong about how much these stellar explosions actually produce? The answer will rewrite the recipe for building a galaxy from the ashes of dead stars. This delicate dust is the raw material for future worlds, but its fate is tied to a far more violent cosmic cycle. The death of a star does not just spread ingredients, it also clears the kitchen. This is the 17th mystery, the enigma of supernova feedback, a process where stellar death governs the very birth of new stars and the growth of entire galaxies. At its heart, feedback is a simple concept of cosmic cause and effect. When a massive star explodes, it does not do so in isolation. It is often born within a vast, dense cloud of gas and dust, a stellar nursery brimming with potential new suns. The supernova's immense blast wave and the intense radiation from the newborn neutron star pour a staggering amount of energy back into this environment. This energy heats the surrounding gas, pushing it away and effectively blowing the nursery apart. It is a form of galactic self-regulation, where one generation of stars dictates the conditions for the next. We see this process in action in a strange and wonderful class of objects known as green pea galaxies. These are small, compact galaxies that glow with an intense and unusual greenish light, a signature of highly energized oxygen gas. They are undergoing ferocious bouts of star formation, but they are also riddled with supernova. The explosions are literally punching holes in the galaxy, driving powerful winds that eject gas into intergalactic space at phenomenal speeds. This is feedback in its most extreme form, a stellar uprising that can actually quench or shut down star formation by robbing the galaxy of the very fuel needed to make new stars. The great mystery is not that feedback happens, but how it works with such precise, large-scale control. The process is not a simple on-off switch, it is a complex, turbulent dance. How can a single, chaotic explosion in one corner of a giant gas cloud influence the collapse of a potential solar system light years away? The energy from a supernova can also have a constructive effect. By compressing nearby pockets of gas with its shockwave, it can actually trigger the gravitational collapse that forms new stars, a process known as triggered star formation. So, does a dying star give life, or does it take it away? The answer is both, and the balance between creation and destruction is what sets the rhythm of a galaxy's evolution. The precise mechanisms that determine whether feedback will gently simmer a galaxy's gas or violently blow it away remain one of the most active and challenging areas of astrophysics. We are only beginning to understand how the death cries of massive stars write the rules for the lives of their descendants. That galactic cycle of creation and destruction leaves behind a specific chemical signature, a cosmic fingerprint that includes the very elements that make our own biology possible. But one of these essential ingredients presents a particularly puzzling case. Phosphorus is a cornerstone of life as we know it. It forms the backbone of our DNA, the energy currency of our cells in ATP, and the structure of our bones. Without it, life on Earth would be unrecognizable and perhaps impossible. Yet, its cosmic origins are shrouded in uncertainty. We do not fully understand how the universe manufactures this vital element in sufficient quantities. While common elements like carbon and oxygen are forged reliably in the hearts of massive stars, phosphorus is a rarer commodity. Its creation requires a more specific and violent process. The leading theory points to a particular type of core collapse supernova, one born from a star with a mass around 20 times that of our Sun. In the final moments of such a star's life, as the shockwave rips through its layered interior, a specific region rich in silicon and oxygen can experience a runaway capture of neutrons. This rapid neutron capture process, operating in a slightly different mode than the one that creates gold, can efficiently produce phosphorus. The key seems to be a neutron flux that is just right, not so weak that it fails to build the element, and not so strong that it pushes past phosphorus to create heavier, irrelevant elements. It is a stellar balancing act of immense precision. This raises a profound question about our cosmic connectedness. Is the phosphorus in our very bones a gift from a specific, relatively common type of stellar death? Or is its production a far more fragile and rare event? Recent studies of the chemical makeup of distant nebulae and ancient stars have revealed a startling variability in phosphorus abundance. Some regions of the galaxy are rich with it, while others are surprisingly barren. This patchy distribution suggests that not all supernovae are equal in their phosphorus production. It may be that only a specific subset of collapsing stars with just the right mass and explosion energy become the galaxy's primary phosphorus factories. If this is true, then the prevalence of life itself could be tied to the specific death cries of certain stars. We are not just stardust in a general sense, we are, in part, the legacy of a very particular kind of stellar catastrophe. The mystery of phosphorus forces us to confront a humbling possibility. The building blocks of life may not be scattered evenly across the cosmos, but concentrated in pockets, delivered by the specific, and perhaps uncommon, deaths of the stars that came before us. Just when we thought we had classified every kind of stellar death, the universe revealed a new kind of monster. In 2018, a celestial event now known as the Cow exploded into view, and it broke all the established rules. It was not a supernova as we knew them. It was something else entirely, a new class of explosion we call fast blue optical transients, or FBOTs. The Cow was staggeringly bright, reaching its peak luminosity in just a few days, while a typical supernova takes weeks. It was also incredibly hot, shining with an intense blue-white light, and it faded away almost as quickly as it appeared. This speed was the first clue that we were witnessing a fundamentally different physical process. A normal supernova's light is powered by the slow radioactive decay of nickel-56, a process that unfolds over many months. The Cow's rapid rise and fall suggested a far more violent and short-lived energy source, like a sudden, catastrophic flare that burned out almost immediately. So what could possibly cause such a brilliant, fleeting flash? One leading theory is that we are seeing a star being shredded by a black hole. In this scenario, a dense, compact object like a white dwarf or the core of a larger star wanders too close to a black hole. The immense tidal forces of the black hole stretch and tear the object apart in a tidal disruption event. But unlike the typical disruption of a star, which can take months, this might be the destruction of a much denser, more compact object, leading to a far more rapid and energetic release of light as the debris is consumed. Another compelling idea is that the Cow was a failed supernova, a stellar collapse that almost formed a black hole. In this model, a massive star's core collapses, but instead of blowing the entire star apart, a powerful jet of material is launched at nearly the speed of light. If that jet is pointed directly at Earth, we see an intensely bright and fast event as the jet breaks through the star's surface and interacts with dense material shed by the star in its final years. The intense blue light and rapid evolution are the signature of this jet slamming into a pre-existing shell of gas. The existence of FBOTs like the Cow forces a radical rethink of stellar death. It suggests there is an entire zoo of explosive phenomena existing in the gray area between supernova and tidal disruptions, events that are too fast and too hot to fit our old categories. Each new FBOT we discover is another piece of a puzzle we are only just beginning to assemble, revealing that the final moments of a star can be far more diverse and bizarre than we ever dreamed. Deep within the chaos of a core collapse, a subtle music begins to play. The newborn neutron star, a sphere of unimaginable density, does not form in perfect silence. It vibrates, oscillating in a complex symphony of resonant frequencies, ringing like a colossal bell struck by the hammer of its own creation. These are its oscillation modes, and each one is a direct probe into the star's deepest secrets. The frequency of the fundamental mode, the star's primary hum, tells us about its average density. Higher overtones, the harmonic shimmers in its tone, reveal the density and pressure profile from its rigid crust all the way down to the exotic matter at its superfluid core. If we could just listen, we could essentially perform a stellar ultrasound, mapping the interior of an object we can never hope to visit. Yet this sound does not travel through the air. In the vacuum of space, the vibrations manifest as rhythmic pulsations in the star's brightness and in the space-time around it. They create tiny, periodic gravitational waves, ripples in the fabric of the universe that could, in theory, be detected by observatories like LIGO and Virgo. The challenge is one of unimaginable scale. The ringing of a neutron star is not a low, mournful chime, but a ferociously high-pitched tremor with frequencies of hundreds or even thousands of cycles per second. Detecting this faint, high-frequency signal amidst the cosmic noise is a monumental task for our current technology. This leads to an even more ghostly possibility. What if the sound of the collapse is not carried by the star itself, but by the very particles it emits? The torrent of neutrinos that floods out carries more than just energy, it carries information. As these ghostly particles stream through the outer layers of the collapsing star, they are subtly imprinted by the material they pass through. Theorists suggest the neutrino signal itself could have an acoustic signature, a faint modulation in its intensity that corresponds to the vibrational modes of the deep interior. It would be a whisper encoded in a hurricane, a message from the heart of the cataclysm written in the language of the universe's most elusive particles. To detect this would be to hear the true voice of a dying star, a direct broadcast from the moment of its transformation. What strange melodies would we hear from a star turning itself inside out? The answer is waiting, a silent song trapped in the next great stellar collapse. That silent song may begin long before the final collapse. Some stars appear to scream out a warning in their final years, convulsing with violent outbursts that tear at their own outer layers. This is the pre-supernova scream, a mysterious phase of activity that challenges our picture of a star's quiet, steady march toward death. We have watched as stars like the famous supernova progenitor SN 2015 BH were observed to erupt multiple times in the decades before their terminal explosion, ejecting massive shells of gas into their immediate surroundings. The cause of these pre-death convulsions is a profound puzzle. One compelling idea points to the final, desperate nuclear burning stages deep within the star's core. In its last months, the core is a layered inferno, fusing successively heavier elements in shells around a growing iron heart. These fusion shells can become thermally unstable, igniting in sudden, violent flashes rather than a steady burn. This explosive shell burning sends powerful pressure waves racing outward through the star's immense bulk. When these waves finally reach the star's tenuous outer surface, they do not break gently. They slam into the stellar atmosphere with enough force to violently eject a portion of the star's own body into space, like a seismic shock from the core blasting the surface away. Another, more exotic theory involves wave heating generated by the turbulent core itself. As the core becomes increasingly unstable, it may begin to oscillate intensely, generating waves similar to the ringing of a bell. But these are not sound waves as we know them. They are gravity waves and pressure waves of immense power. They transport a colossal amount of energy from the convulsing core to the cooler outer envelope, dumping their heat and causing the star's surface to bloat and erupt. It is as if the star's dying heart is sending out feverish pulses that literally make its skin blister and peel away. What triggers these specific instabilities remains unknown. Is it linked to the star's initial mass, its rotation, or its chemical composition? Each pre-supernova outburst is a crucial clue, a vital piece of the timeline that connects a star's long, stable life to its instantaneous, catastrophic death. Understanding this final, frantic chapter could give us the ability to predict which star will explode next, turning the cosmos from a theater of surprise into a book we are finally learning to read. A star's final moments are not always a solitary affair. For many massive stars, death is a dance with a partner, a gravitational tango that can twist a predictable collapse into something far stranger. This is the 22nd mystery, the role of binary companions, where a nearby star can steal, shove, or even merge with its neighbor to rewrite the rules of stellar death. The most common alteration is a process of cosmic theft. In a close binary system, one star can gravitationally siphon the hydrogen-rich outer layers from its companion, slowly stripping it bare over millions of years. The victim star is left as a naked, hot helium core, its protective gaseous envelope gone. When this stripped star finally runs out of fuel and collapses, the resulting supernova is fundamentally different. Without a massive hydrogen blanket to blow off, the explosion lacks the characteristic bright, long-lasting signature of a normal supernova. Instead, we see a fainter, faster-fading event known as a type Ib or Ike supernova. It is a quieter, more efficient death, one that would have been impossible without a thieving partner, but theft can escalate to a far more dramatic conclusion. If the two stars are locked in an exceptionally tight orbit, their gravitational interaction can spiral them toward a violent merger. As they circle each other, they lose orbital energy through gravitational waves, drawing inexorably closer until their outer layers touch. What follows is a chaotic, fiery confluence. The two stellar cores plunge together, triggering a massive injection of fresh hydrogen fuel into the primary star's core, or creating a single, rapidly spinning and violently unstable superstar. This merger can instantly push a star that was below the supernova mass limit over the edge, forcing a premature collapse. Alternatively, the immense spin from the merger might be the crucial ingredient needed to power a hypernova and a long gamma-ray burst, an event typically reserved for rare, solitary giants. The presence of a binary companion solves some puzzles, like the missing progenitor stars we cannot find in pre-explosion images, but it creates new ones. How many of the supernova we see are the product of these stellar duos? Could our entire understanding of stellar life cycles be skewed because we have underestimated the prevalence and influence of these cosmic partnerships? The death of a star, it seems, can be a family matter, a final act shaped as much by a companion's pull as by its own internal fire. Our cosmic census of stellar death reveals a troubling gap. We look at a bustling galaxy like our own Milky Way, a sprawling metropolis of hundreds of billions of stars, and based on our understanding of stellar life cycles, we predict it should host a core collapse supernova roughly 2 or 3 times every century. Yet the historical record is strangely silent. The last time a naked-eye supernova was seen in our galaxy was by Johannes Kepler in 1604. This is the supernova rate problem, a glaring mismatch between the number of stellar explosions we expect and the ones we actually witness. Where are all the missing supernova? One simple yet profound possibility is that we are just not seeing them. A supernova's brilliance can be dimmed by the very dust and gas that fills the spiral arms of our galaxy. If an explosion occurs on the far side of the galactic center, shrouded behind vast interstellar clouds, its light could be completely absorbed before it ever reaches us. We would be living in a city where fireworks are constantly going off, but we only see the ones that happen in our own clear neighborhood. This is the dust-hiding hypothesis, a cosmic game of peek-a-boo where the galaxy itself acts as the ultimate obscuring curtain. But could the problem run deeper than mere visibility? Perhaps we are missing an entire population of faint supernova. We have already explored how stripped envelope stars in binary systems die in quieter, less luminous explosions. What if there are other, even more subdued ways for a star to die? Some theoretical models suggest that for certain stars, the collapse might be so inefficient, the explosion so weak, that it barely makes a blip on our cosmic radar. The star still dies, but it does so with a whimper, not a bang, leaving behind a neutron star or black hole without the spectacular optical display we associate with a classic supernova. This would mean our telescopes, tuned to find brilliant flashes, are systematically ignoring a whole class of stellar funerals. The most unsettling possibility, however, is that our foundational models are flawed. Our predictions rely on a precise understanding of the initial mass function, the rule that governs how many stars of each mass are born. We assume we know how many massive, short-lived stars exist in a galaxy at any given time. But what if the universe is not making massive stars at the rate we think it is? Or what if many massive stars end their lives not in a core collapse, but by silently imploding into a black hole, a process known as direct collapse, which produces no visible supernova at all? This would mean our entire count of potential supernova progenitors is wrong. The supernova rate problem is more than a simple accounting error. It is a direct challenge to our understanding of the galactic ecosystem. Every missing explosion is a question mark over the life and death of stars, forcing us to wonder if the cosmos is far quieter in its dying moments than we ever believed. Just when we thought we had seen the limits of stellar violence, the cosmos unveils an even more brilliant class of detonation. Superluminous supernovas shatter all previous records, outshining their ordinary cousins by 10, 50, even 100 times. These are not merely bright explosions, they are cosmic beacons of staggering power, and their existence forces us to confront a new mystery: where does all that light come from? A normal supernova is powered by the decay of a sun's worth of radioactive nickel, but to achieve such phenomenal brightness, a superluminous event would need to synthesize and eject a truly monstrous amount of this isotope, perhaps several times the mass of our entire sun. The physics of such prolific nickel production seems almost unachievable, pushing the limits of what we believe a collapsing star can do. This has led theorists to a second, more dynamic possibility: a central engine. Imagine the newborn neutron star is not just a dense cinder, but a rapidly spinning magnetar, a stellar corpse with a magnetic field 1 trillion times stronger than Earth. As this cosmic powerhouse spins, its immense magnetic field acts like a colossal brake, converting its rotational energy into a torrent of radiation and high-energy particles. This continuous injection of energy from the inside acts like a bellows on a fire, keeping the expanding supernova debris hot and luminous for months, long after a normal explosion would have faded. It is a slow, powerful burn rather than a single blast, yet there is a third compelling theory that places the power source not in the core, but in the star's final history. Many massive stars undergo violent convulsions in their last centuries, shedding their outer layers in titanic eruptions. If the eventual supernova blast wave plows into this pre-existing, dense shell of circumstellar material, the resulting collision would be apocalyptic. The kinetic energy of the expanding debris is converted almost instantly into an immense flash of light, creating a secondary explosion that can dwarf the initial collapse. Each of these theories paints a different portrait of a star's final years. Was it a prolific producer of rare elements, a rapidly spinning magnetic monster, or a convulsive giant that shrouded itself in its own funeral shroud? The answer may be that all three occur, each representing a different, extreme path to a superluminous end. Even a star's total annihilation might not erase its story. When a massive stellar core collapses into a black hole, it crosses a threshold of no return, the event horizon from which not even light can escape. According to Einstein's theory of general relativity, the black hole that forms is defined by only 3 simple properties: its mass, its electric charge, and its spin. Every other detail about the star that formed it, the intricate pattern of its iron atoms, the specific swirls of its magnetic fields, the very identity of the trillions upon trillions of particles that constituted it, all that information seems to be utterly and permanently destroyed. This presents a direct and profound conflict with the foundational principles of quantum mechanics, which state that information is never truly lost. In the quantum world, the state of a system is always, in principle, reversible. You should be able to run the cosmic film backward and see the star reassemble itself from the Hawking radiation the black hole emits. This is the black hole information paradox, a battle between our 2 most successful descriptions of reality, and it suggests one of them must be fundamentally wrong. One radical resolution proposes that the information is not lost inside the black hole, but is somehow smeared across its event horizon, encoded in a mind-bogglingly complex way on its two-dimensional surface. Another, even stranger idea is that there is no interior, that the collapsing star effectively halts at the event horizon from the perspective of the outside universe, creating a frozen, two-dimensional shell of information often called a firewall. The paradox forces us to ask a deeply unsettling question about the nature of reality itself. Does the universe truly forget, or is every detail of a star's existence preserved forever, scrambled into a code so perfect we have not yet learned to read it? The death of a star may not be an erasure, but the ultimate cosmic encryption. The silent song of a collapsing star sometimes ends in a duet of pure destruction. When two neutron stars, the ultra-dense corpses of past supernova, are locked in a final orbital embrace, their collision solves one great mystery while birthing several more. For decades, the origin of the universe's heaviest elements was a subject of intense debate, but in August of 2017, we finally witnessed the answer. The LIGO and Virgo observatories detected the faint ripples in spacetime from such a merger, and telescopes across the globe swiveled to observe the aftermath, a brilliant, fast-fading glow we call a kilonova. The light from this event was rich with the spectroscopic fingerprints of lanthanides and other heavy elements, definitively proving that these cosmic crashes are indeed one of the universe's primary forges for gold, platinum, and uranium. The confirmation was a monumental triumph, yet it immediately exposed deeper layers of uncertainty. We now know these mergers create the elements, but the precise physics of how they do it remains shrouded in chaos. The merger itself is an event of almost unimaginable violence. Two city-sized objects, each more massive than our Sun, spiral together at a significant fraction of light speed, tidally tearing each other apart in a matter of milliseconds. The details of this process, the exact behavior of matter at these extreme densities, is something our most powerful supercomputers still struggle to simulate. What happens in the first seconds after contact determines everything from the amount of heavy elements synthesized to the ultimate fate of the merged object. This leads to the most tantalizing mystery of all, the brief and unstable existence of the hypermassive neutron star. For a fleeting moment, the two stellar corpses merge into a single, monstrous object. It is not immediately a black hole. Instead, it forms a rapidly spinning, teardrop-shaped mass that is supported not just by neutron degeneracy pressure, but by its incredible rotation and thermal energy. This hypermassive neutron star is a transient giant, a temporary state of matter that pushes against the absolute limits of physics. Its lifetime is terrifyingly short, perhaps only a few hundred milliseconds before its own immense weight, now far exceeding the stable neutron star limit, overwhelms all supporting forces. The precise properties of this object, its exact mass, its internal temperature, and the strength of its magnetic fields, are what control the entire kilonova explosion. It is the central engine that powers the outflow of neutron-rich material, the very stuff that rapidly captures neutrons to become gold and platinum. Yet we cannot see it directly. It is hidden deep within an opaque cloud of debris and is gone in the blink of an eye, leaving behind only the elemental signature of its spectacular collapse into a black hole. Each kilonova we detect is a brief window into this ultimate pressure cooker, a chance to understand the final, unstable heartbeat of matter before it vanishes forever into darkness. Even the most reliable rules of the universe might bend under the strain of a dying star. This leads us to a truly radical mystery, one that questions the very bedrock of physics. Could the fundamental constants of nature, the fixed numbers that govern the strength of gravity or the power of electromagnetism, actually change within the unimaginable densities of a collapsing core? We have always assumed these constants are, as their name implies, constant everywhere and forever. But what if the crushing pressure inside a neutron star or the searing heat of a supernova creates conditions so extreme that the rules themselves begin to warp? Studying these stellar catastrophes provides us with a unique cosmic laboratory, one we could never hope to build on Earth. For instance, the precise balance of forces that determines the maximum possible mass for a neutron star is exquisitely sensitive to the strength of the strong nuclear force, the glue that holds atomic nuclei together. If we observe a neutron star with a mass that seems impossibly high according to our current constants, it might be a clue that in that ultra-dense environment, the strong force operates just a little bit differently. Similarly, the brilliant light from a supernova carries a specific signature of atomic elements forged in the blast. The energies required to create these elements depend directly on the fundamental constants. By analyzing this cosmic fingerprint with immense precision, we can check if the laws of physics that ruled the star's death match the laws we measure in our quiet corner of the galaxy. It is a test of reality's consistency on the grandest stage imaginable. What if a dying star does not just test the laws but temporarily rewrites them? The answer would reshape our understanding of everything from the first second of the Big Bang to the ultimate fate of the cosmos. The most unsettling stellar disappearance is a silent one. A massive star simply blinks out of existence, leaving behind no brilliant explosion, no expanding nebula, no cosmic fireworks. It is there one moment and gone the next, vanishing from our telescopes as if it had never been. This is the hypothetical dark supernova, a total stellar collapse where a star skips the supernova stage entirely and implodes directly into a black hole. For such a cataclysm to occur, the star must be truly monstrous. In its final moments, the core collapses just as it would for a normal supernova. But the outgoing shock wave, the one that should rip the star apart, never makes it out. It stalls, overwhelmed by the sheer torrent of material falling inward from the star's own immense weight. Instead of rebounding, the entire stellar structure, core and all, continues to collapse. The event horizon forms deep inside the star and rapidly expands outward, consuming the entire star from the inside out. The star is literally eaten by the black hole it just gave birth to, and the only signal left behind is a brief, final flicker of neutrinos and a profound, permanent silence where a star once shone. We have a handful of tantalizing candidates for this cosmic vanishing act. In 2008, astronomers were watching a giant red supergiant known as N6946bh1. It was a stable, well-studied star shining predictably for years. Then, within a few months, it simply faded from view. Subsequent searches with the most powerful telescopes, including Hubble, found nothing. The star was gone. No supernova was ever detected at that location. It is as if the star turned off its own light and slipped away into the dark. The challenge of confirming this theory is immense because we are searching for something that, by its very nature, leaves almost no trace. How do you prove a star disappeared without a bang? You must first have a reliable before picture, a confirmed observation of the star in its healthy state. Then you need to rule out every other possibility. Could it have been a supernova imposter that ejected a thick dust cloud, temporarily hiding itself? Could it have been a faint, unusual supernova that our survey simply missed? To build a case for a direct collapse, we need to see more of these disappearances and gather more evidence, perhaps catching the final, subtle dimming as the star is consumed. Each candidate event is a ghost story written in the language of missing light, forcing us to confront the possibility that the most complete stellar deaths are the ones we never see at all. The collective death of stars writes the final chapter of galactic ecology. When a cluster of massive stars live and die together, their sequenced supernova create a force of cosmic upheaval known as a galactic fountain. This is not a gentle spring, but a titanic geyser on a galactic scale. The combined energy from multiple explosions, sometimes hundreds or thousands of them, can blow a colossal bubble in the interstellar medium. This superbubble, heated to millions of degrees, becomes buoyant. It punches through the cooler, denser gas of the galactic disk and erupts into the galactic halo, a vast, sparse region high above the starry plane. For millions of years, this fountain of hot, metal-rich gas arcs outward, a slow-motion eruption of stellar ashes traveling thousands of light years into the void. The journey, however, does not last forever. As this ejected material travels through the halo, it gradually radiates away its heat. It cools, condenses, and loses its buoyancy. Under the relentless pull of the galaxy's gravity, the now cooler clouds of gas begin to fall back, raining down onto the galactic disk like a cosmic waterfall. This entire cycle, from explosive ejection to gravitational rain, is the galaxy's primary method of recycling its own building blocks. The mystery lies in the profound regulation this process imposes. This galactic fountain is the great mixer of the cosmos. It scours the interstellar medium of the heavy elements forged in supernova and flings them far and wide. When this enriched material falls back, it does not return to its point of origin. It seeds entirely new regions of the galaxy with the elements necessary for rocky planets and, ultimately, life. It prevents the galactic disk from becoming a stagnant, polluted pond, instead keeping it a vibrant, churning sea where new stars can form from well-mixed, enriched gas. Yet the details of this cycle remain elusive. How much gas is truly lost to intergalactic space forever, and how much faithfully returns? How does this falling rain of cold gas influence the formation of the next generation of stars, and does it trigger or suppress their birth? We are only beginning to understand how this majestic billion-year cycle, driven by stellar death, governs the health and evolution of entire galaxies. Even these cosmic diamonds are not eternal. Across timescales that dwarf the current age of the universe, the ultimate fate of a neutron star unfolds in a slow, cold drama. The first path is a gradual dimming into oblivion. A newborn neutron star blazes with the heat of its violent birth, but over trillions of years, it will radiate that energy away into the void. It cools from a blazing ember to a cold, dark crystal of pure nuclear matter, a black dwarf in its most extreme form. This stellar corpse would drift silently through a galaxy grown dim, its internal clock having effectively stopped. Yet in this profound cold, a final, spectacular detonation might still be possible. This is the concept of a black dwarf supernova. In the far, far future, the slow, relentless process of quantum tunneling could theoretically trigger a runaway fusion reaction in the star's ultra-dense carbon and oxygen ash. After eons of silence, the dead star would suddenly resurrect in a final, brilliant flash, the last supernova in a dying cosmos. But there is a second, more unsettling possibility rooted in the deepest laws of physics. What if the very fabric of the neutron star is not stable? Our current models assume the proton is stable and lives forever. But many grand unified theories of physics predict that the proton itself must eventually decay, with a half-life so immense it is beyond human comprehension. If this is true, then every neutron star is slowly dissolving. The neutrons and protons that form its incredible structure would, over an unimaginable timescale, spontaneously break apart, their constituent quarks decaying into lighter particles. The neutron star would not explode, it would simply and slowly evaporate, fading from existence like a cosmic ice cube sublimating in a dark room. This final mystery forces us to confront the limits of matter itself. Will the universe's most perfect diamonds shine in a final, defiant flash, or will they simply vanish into a silent, slow-motion rain of particles? The answer depends on physics we have not yet mastered, on the true stability of the universe's building blocks. The final legacy of a collapsing star may be to illuminate the ultimate fate of all matter, a secret held in its cold, dense heart for a time longer than stars themselves will burn. From the silent trigger of collapse to the final evaporation of a cosmic diamond, This journey through 30 mysteries has revealed a universe in constant, violent flux. We have stood at the precipice of stellar death, witnessing the ghostly neutrino burst, the violent asymmetry of the explosion, and the birth of elements that make our own existence possible. We have confronted silent failures, brilliant imposters, and the profound possibility that the laws of physics themselves may bend within a dying heart. And yet, with every answer we uncover, the cosmos responds not with an ending, but with a deeper, more intricate question. The solved mystery of neutron star mergers as a source of gold immediately opened the enigma of the hypermassive neutron star's fleeting life. The confirmed identity of a progenitor star only highlights the countless others that vanish without a trace. This is the relentless engine of discovery, where each solution is not a destination, but a new starting point, a doorway into a darker room filled with even more dazzling puzzles. So the next time you look up at the quiet night sky, remember the hidden chaos. Remember that within that apparent stillness, stars are living and dying in spectacular fashion, forging the very materials of worlds and life. Your place in this cosmos is tied to those distant cataclysms. Stay curious, for the next great revelation, the one that rewrites our understanding of reality, is waiting. It is encoded in the light of the next dying star, a mystery just beyond our current grasp, inviting us to look deeper and ask the next great